Hello and welcome to today's webinar. It is the first tutorial in our series about distance protection. My name is Jose Malagon and I'm a technical consultant for process bus and power system stability. Today I'm the moderator and I have the honor to guide you through this webinar. So, distance protection, what is it? How does it work? Why do we use it? Where do we use it? A lot of questions that I'm sure will be answered in today's session. The expert presenting the topics today is my dear colleague and master, Mr. Gustav Steinberg. I'm sure he is already well known as, or I guess I can say, as the expert for line protection. Of course, you will have the chance to ask questions. You can type your questions in the questions field or in the chat during the whole webinar. And I will be your voice and read the questions to our expert. We will have 2 short breaks. Q&A sessions are planned before the breaks and at the end of the session. All the questions that we won't answer today will be answered after the webinar in a written format. So please don't hold back and ask everything you want to know about the distance protection. Now I'm happy to hand over to Gustav, and he will start with the first part of this interesting training. Welcome, Gustav.
Thank you very much, Jose, and welcome from my side to all of you. I hope I'm not a new face to everybody, but to those that don't know me, I hope that you will remember me after this presentation. Distance protection has been a hobby of mine for a long time, and I was thinking how to explain it in a presentation in a relatively short time. And I said, let's do it with some questions and answers. And I think what is the typical question you will have would be what is a distance protection? For some of you that would be an easy answer and you would say, I know, but maybe it's a good time to rethink it. What you know probably if you know anything about distance protection, it's fairly complicated. So the question then is, why would we use something that is so complicated? And that I will try to explain the real big advantage of having a distance protection. And then finally, a little bit, how does it work? Because if we're going to use it, we need to also know how it works. So at that point, let me go straight into the question, what is a distance protection? If we look at this little diagram here, you can see it shows a little bit the history, and sometimes I worry because I'm not so young anymore that my life covers almost half of this. Electricity has not been around for so long if we think about humanity, but in this diagram you see in about 1910 protection was first used by Siemens, and the distance protection was part of this from a very early time, probably almost completely on the left-hand side in that diagram. Now around about 1920 we have in the 1920s the first reference to distance protection. So it has been with us a long time, so it shows that it is an important function, and otherwise it would not have been there at that early stage. So if we look at this diagram now, what is it? The distance protection is a protection that, as you can see here, measures current and voltage. And then probably at the lower diagram you see there are some zones that are applied, and you are trying to establish is a fault in a certain area or not. And this is going to be very important for a selective protection, and that is the ultimate purpose of protection, to achieve selectivity. So basically distance protection is going to measure current and voltage. It's going to use, as you see at the top, an impedance principle to establish, to localize the fault location. That's why sometimes impedance protection, distance to fault, localize the fault, identify which area it is in, and then make a trip decision. And very important in this trip grading for the selectivity is also time. So you can see the time criteria, we have certain zones with time delays. That in a nutshell is what distance protection is. From the early days, we saw earlier on the diagram, I say in the early 1920s, we did not have any electronics as such, transistors and that type. At that time it was electromechanical. And you see a little diagram here showing how roughly in a schematic way a distance protection was constructed. You have see there's 2 windings, a current and a voltage winding. As you see, the 2 measurements we used previously for the impedance protection. And the current would be the operating criteria, say pulling down to try and close the trip contact, and the voltage is a restraint criteria preventing the pivot of this axis over here. So voltage, restraint, current, operate, and a little spring at the top, you see the control spring, would be kind of setting a characteristic. And like that, you can construct a very, very primitive or very simple distance protection. And if one uses very quality electromechanical equipment, you can get a very high quality protection. If we now apply that to try and get a selective tripping, we have to come to the other issue we see at the bottom left-hand side, the zones. So we classify for the distance protection, we have to apply a characteristic, and in the old days, electromechanical, you would have to construct two characteristics. It will change a method of operation to have an element, a measuring element, and the measuring element would have a boundary, and the boundary would be a zone. And we'll see that a little bit later on in the other descriptions as well. So ultimately, you identify a zone, and the zone would operate for faults in a certain area, and another zone in a different area, and that together with time grading is going to achieve the selectivity. So ultimately, you can see here, the purpose is to trip on the F1 with this relay and not to trip on the F2. That is going to be the ultimate objective that the distance protection will achieve. And we'll see how that is done later on. The characteristic we just saw, the electromechanical one, this very simple one I showed here, ends up with a circular characteristic. And this is interesting. We'll see the circular characteristic later on as well. And often in literature, you see these diagrams. And we'll also look at one particular circular characteristic, the MO, a little bit later on. And that is the result of this method here. Why is it such a simple characteristic? Because obviously, if we're going to apply this method here, it is a simple magnitude comparison over here. Because the basically going through the iron here, you're going to get an average response, and that is going to then rectify it, and you will not have any phase information. You see the two equations on the left-hand side. The top is the Z, the complex impedance, as we'll see later on in numerical relays. And at the bottom is the magnitude. You simply, like an electromechanical relay, would have a magnitude response and only give you a circle. So you would not know where in the circle the impedance is, but you know it's somewhere inside the circle or outside. It is not directional. This is obviously a big risk constraint, because if we don't know if the fault is forward or reverse, then in terms of selectivity, we have a big problem. All right, so a directional characteristic will be added, and this, I show this here as a highlight, because even today, in the most modern distance protection relays in microprocessor, we do still apply this principle of doing the directionality as a separate measurement to the reach. The reach measurement, which is inside the circle or outside, is done together with a separate direction measurement. The direction measurement has got other prerequisites or other demands that it has different to a reach measurement. That's why it is done in two measurements, and you combine them to get the ultimate characteristic here, as is shown as a graphic example here, to make the circular characteristic directional. All right, now we come, after clearing up what the what is, a distance protection is, why do we use it? As we saw now, it is not the simplest technique, so we must identify why would we do something like that. And I have a couple of diagrams to show that, because if you look at this situation here, the classic selectivity, tripping on the internal fault and not tripping on the external fault, is the requirement. And the distance protection can achieve this. And I'll show later on that other techniques like an overcurrent cannot achieve this. That is why we're using a distance protection. This example here, you can see the top and bottom, the two circuit diagrams represent a symbolic, are identical, except for the situation that you have that the green arrow shows you that at the top left-hand side you have the breaker closed, and at the bottom left-hand side the breaker is open. So it is the same system conditions, except for one switching operation, which can happen at any time. And in terms of a protection, if you now look at where I localized the protection relay there, the distance relay in blue, the blocks you can see down at the bottom here, and the same in the other diagram. For that protection, for the external fault at the bottom here, this F2, you can see that the current is 12 kiloamps about, because it's all flowing in the bottom feeder, the top path is closed, is open, sorry. And in the other diagram on the top here, you can see the breaker is closed, and is on the internal fault only 10 kiloamps long. So an overcurrent protection, if that 21, this distance relay, were an overcurrent relay, it would not work correctly, because it sees 12 kiloamps on the external fault and only 10 kiloamps on the internal fault. So Knowing overcurrent protection, it will not achieve a selectivity over there. A distance protection will achieve that, and we'll try and show that in a couple of diagrams now. For this ultimate, well not say ultimate, for this distance protection selectivity, all you need is two zones. And these two zones are classified as normally we call it the zone 1, an underreaching zone, and you have an overreaching zone, the zone 2. And they have two very clear requirements. The underreaching zone, zone 1, requires here a safety margin. And the safety margin is, as we'll see later on, to allow for tolerances. So it may never pick up on an external fault. This is so you need a safety margin to see if the fault is on a remote bus bar or further away. It may not pick up. And the other zone, the zone 2, is our overreaching zone. It must cover the complete line. So it has a security margin here to make sure that it will always see internal faults. It will not fail to pick up on an internal fault. This is the two basic definitions of a zone 1 and the zone 2 as we are going to use it in this example. All right, we're going to go through a simple series of slides now to explain how the distance protection is going to get a selective fault clearance of this fault over here. We have the line at the top, AB, and that's the faulted line, and the bottom line is shown protected in the same manner, and it will also respond. Now, because we saw the directionality is given on the bottom feeder, there will be no pickup on the right-hand side. There will only be a zone 2 pickup on the left-hand side, because obviously the zone 2 is overreaching and would see beyond the line and would pick up on that fault B. Is that a problem? We'll see not really, because initially what we will have picked up is the zone 2 at the bottom, as we just explained, and on the top, the zone 1, obviously on the right-hand side, and on the left-hand side at A, we will have the zone 2 pickup. The pickup takes a certain time. I showed it at the top, around about 20 milliseconds is roughly the pickup time. So all these three relays will pick up in these 20 milliseconds. With the time grading, only the zone 1 is going to issue a trip now. So in this stage, now after that zone 1 pickup will result in a trip. That trip will go to the breaker. The breaker has a certain response time. I showed it here, about 3 cycles. So it takes at 50 hertz. So at 80 milliseconds, the breaker at B is open. First step, so good, and you can see where this is going, because when this breaker at B is open, the zone 2 over here will no longer be seeing the fault. Now you go into the reset time. The zone 2 is going to have a drop-off time, again approximately 20 milliseconds. Zone 2 at the bottom will be dropped off, and then the zone 2 timer at the top, it will be running. Will run time out. Typical time grading is around about 250, 300 milliseconds, and then here after the timeout, this zone 2 at A is going to trip, and we will see with the reset at the bottom and the zone 2 trip at the top, the fault is cleared selectively. And that is essentially how a selective distance protection in its most basic form will work and can achieve this. And there is, if you change the in-feed conditions, there is no other protection function that can do this. You cannot depend on differential protection, because it's communication related. If we add you don't have any communication here. You cannot do it with overcurrent protection or any other protection. So without communication, for selectivity, you need distance protection. And just to summarize again, the important aspect, the zone 1, remember, needs the safety margin. It must underreach. It may never pick up on the external fault. And the zone 2 needs a security margin. It must cover the feeder. That's the fundamental requirement of those two zones. All right, having now looked at what and why, we now come to the third question, which is how. Okay, and there we can spend a lot of time, but I obviously choose a few examples for the how. And the first one, again, going maybe to the electromechanical comparator, but that was replaced by electronics a little bit later. And you can see here now, instead of the electromechanical operator, we have now an electronic comparator here, but in principle, it is still operating in a very similar manner, this comparator. And it uses the principle of converting the measured current to a voltage via a replica impedance. And this is a very basic method of a distance protection. This replica impedance corresponds to the zone setting. So it is an impedance, and if you convert it now to primary and secondary, we'll see later on, the importance of understanding what is a secondary impedance and a primary impedance. Obviously, over here we are working with secondary components, secondary current and secondary voltage, so we are here in the secondary world, but that can be converted to primary. So if we say this impedance here, this replica models the primary zone boundary, then we can imagine if a fault were at the zone boundary, and this is going to be interesting, then based on this model, the voltage you measure here would be equal to the voltage you get across the replica impedance, because this here is modeling what is happening on the primary side. If the fault is at the zone boundary, which corresponds to the Z replica impedance, then by Kirchhoff's voltage loop, the voltage here created on the secondary side must equal the measured voltage here, because it is a model of what's happening on the primary side over here. And correspondingly, if the fault is closer, what will happen is that this voltage here will be larger, the current quantity is bigger, it's the operate quantity, and the voltage will be smaller, and the comparator will say inside and give you the trip. And very interesting, it's a circle again. This is obviously doing exactly the same as that electromechanical bridge effort did over there, and the characteristic is a circle. So having come back to the circle, even with this electronic comparator here, I decided let's maybe look at the most famous circle we have in protection, and that is the Mohs circle. Now you can see this interesting thing here. The Mohs circle is copied from the manual. This diagram, you may have seen it before, is offset. It's including the origin over here, and this will explain this a little bit later. This is a memory or voltage polarized, memory voltage polarized or quadrature polarized Mohs circle. This polarization gives it this directionality. Now initially you can think, but if it's including the origin is non-directional, we see later on that this Mohs circle is dynamic. It shifts depending on the fault location. So how does one create such a circle that is now not the circle we saw previously around the origin, but a shifted circle as such? And how does one measure this with a fairly simple function? Because this was already also implemented with electromechanical relays. This can be implemented with electromechanical, and analog does not need a numerical device and was used very extensively early on. What you see now here is this Mohs circle, now not offset. Basically, it is through the origin. This is the classic Mohs circle, not offset. It's a self-polarized Mohs circle, we can say. And how does one do this? Okay, how does a distant projection do this? And this is simply, again, a comparison of voltage signals. You can see there are 3 voltage signals that create the circle, and they create a triangle over here. And these 3 sides of this triangle are the interesting one. The most important one is the diameter here. You can see the diameter of the circle is very, very important. And that is our I times Z replica. As we saw earlier on, that current flowing through the replica impedance is this blue one here. This would be our operate quantity, so to speak. The other quantity you see now here is the measured voltage. Okay, and it's interesting. Before we were just making a balance between those 2, blue and white, and that was a non-offset circle. But now we do something creative. We create this orange phasor here, and this orange phasor, interesting, is this difference. It's this IZ, the blue phasor minus the measured voltage. All right, and this gets this. And now we use an interesting technique, is that you know from your trigonometry in school, if you take a circle and you make a diameter, then any triangle with a point over here on the circumference of the circle will have a 90-degree angle over here. This is a definition. You can move this to any point here, this triangle point here. If as long as it's on the circle, the angle will be exactly 90 degrees. And that we can use. So the definition of this triangle is the fundamental definition of the Mohs circle. You can see this here, the triangle now is defining the Mohs circle. And this boundary condition here, 90 degrees. So interesting to see how will the characteristic now work. It's going to just simply check this 90 degrees over here, because you can see if the fault is inside, the angle is larger than 90 degrees, and if the angle is outside, sorry, the fault is outside, the angle will be smaller than 90 degrees. And this is very advantageous to us because checking an angle is much simpler than it seems. Checking an angle is simply checking time. At 90 degrees, at 50 hertz, 90 degrees equals 5 milliseconds. Right, and so what you do is you take your waveforms, which are the voltage waveforms, we are on those phasors, and we basically turn them into a square wave by just running through a comparator like that. Then you take the two square wave of which you want to compare the angle, and you overlap them through another comparator, and you get basically the interval of overlap over here. And this interval of overlap is the definition of the angle. Over here we have an angle which is larger than 90 degrees because the overlap is larger than 5 milliseconds. So that's a very simple way of measuring an angle. And you can run that here through this diagram over here, all with discrete electronic components. And this is how the Mohs circle was done in older relays. In numerical relays, it's done obviously with microprocessors more effectively, but in essence, it's the same technique that you are doing. Just taking the voltage and this IZ, take the difference over here. You can see in that IZ, you rectify the IZ and you compare it to the measured voltage. That's the angles. Then you do the angle comparison here. And then if the angle is larger than 90 degrees, basically the time will be bigger than 5 milliseconds. The angle is smaller than 90 degrees, it will be smaller than 5 milliseconds. So if the time 5 milliseconds expires, then it was inside, it had a large angle. If the time is 4 milliseconds, for example, it's extra, you won't get a trip. So if the time, only when the 5 milliseconds expires, you are inside the characteristic. Very simple way of doing that. The problem is, this Mohs circle is running through the origin. So this is where the relay is located. So if you have the forward or reverse fault, it is on the boundary. And this is not good because the fault right in front of the relay is right on the boundary and you don't have a dependable operation. That's why the Mohs circle is offset. Remember the situation of adding a directional characteristic after doing the reach characteristic. And it's essentially the same thing here, only in the Mohs, it's all mixed up together and it is one combined measurement now. So to add the directionality, the Mohs circle is offset. Okay, and the offset is done by adding a polarizing voltage to the measured voltage. So remember we had the measured voltage which was from the blue to this origin over here, and we just shift this measured voltage by adding to it a certain portion of memory voltage or healthy phase voltage, a polarizing quantity to that. Okay, and I'll see another example here. You can see in this example that there is the memory voltage. The memory voltage was the fault voltage before the fault, a healthy voltage before the fault occurred. It should essentially have pretty much the same angle as the measured voltage. You can see the little yellow voltage here, the measured voltage during the fault. During the fault, the voltage collapses to a much smaller value. But it's important, the polarizing voltage should have essentially the same angle as the faulted voltage. We'll see that later on as well, that is in a conventional electrical system that will be the case. Now we don't add the full memory voltage, but that would, imagine if you did that, you would have a really huge circle here because it would shift the circle here, not only to that point, but down here. We add a percentage. We'll see that as a setting even just now. On the left-hand side, it's zoomed in to just show you the expansion. The measured voltage and then the expanded polarizing voltage is the measured voltage plus the polarizing voltage, Vmem, memory voltage in this example. All right, just to clear it up for you, a photograph or screenshot from the manual again to just take away your worries that the Mohs circle is not going to be properly selective at the near fault. If the fault is forward, the expansion is as you see, but if the fault here is reverse at this point, then the Mohs circle expansion is there, because obviously if the fault forward reverse here, the current reverses direction. Remember we have the IZ, through a replica impedance that will change its direction, and that means that the expansion is then not, during forward faults you will expand, during reverse faults it's the opposite direction. You get a shrinkage due to the polarization. So you get a very dependable directional criteria with the polarized Mohs circle. And in order to achieve this polarization here, you can see there are settings. It's now, we're starting to see here some settings from the relay. The screenshot again. In the graphics, if you look at the graphics in Dixie, you'll see the self-polarized Mohs shown there, but you won't see the polarized. The Mohs circle is always shown in this manner, as you see in the diagram here. You never really see a graphic of the expanded Mohs, but really one has to know that in reality, during the fault, the Mohs circle is expanded. And the amount of polarizing, you can see here, we've set here in this example, it's a default setting 15%. And you can see it's memory voltage, and we are dual polarized. We're polarizing with memory voltage and healthy phase cross polarization. We'll see a little bit more about what healthy phases are later on in this presentation. All right, enough of the Mohs circle, but the Mohs circle is not really a characteristic we recommend. It is just a historical, because remember we are looking at what distance protection is. That's what we're on about. And so moving forward now to numerical relays. Numerical relays are now, we saw the electromechanical, we saw the Mohs circle created with maybe an analog electronic environment. Now with numerical relays, we have a different approach. In the numerical relays, you will take the signals. We see here our signal shown symbolically here as a sine wave, and we'll sample it, sampling it at certain intervals, and then digitize it. It goes into a digital, so for the microprocessor to compute it, it is digitalized. So you have sampled every individual sample there. And then that is not really that helpful yet, but now you can work with and sampled value algorithms, normally not preferred because you prefer to run this through a filter, but the filter will take away some disturbances and so on, and kind of smooth out and reduce your error susceptibility. And then one combines this filtering technique immediately also with extracting what we need, and that is this phasor. So you basically run it through an orthogonal filter. I don't want to do filter theory. There are different techniques of doing this, but the advantage of the orthogonal filter technique is that you get directly out two components. The two components are the example here, real imaginary component, the quadrature components of the phasor. So you can define, extract from an analog signal here through this quadrature orthogonal filters here, a phasor. And that is really a big thing. Because remember right at the beginning we had the diagram here, or the equation, and we said we could not make this complex division. Now we can, because now we have the complex phasor, voltage current with angle and magnitude, or shown here in its quadrature components. There's just the filter characteristics here. I think we don't need to discuss that much. The signal has got some distortion, this filtering. One has to be careful how one constructs these filters, because you can see there's a current waveform. Current waveform at default has a DC offset. And you can see in the purple waveform, there is some filters, need some transients. They swing in, they don't come to the best result immediately. And one optimizes, it's a science on its own to optimize filtering characteristics. But the advantage really is if we do this with a microprocessor relay, we can, at the end, with this result, essentially do almost anything. And you can see here, we come to a really complex equation, but it's shown here symbolically because it is now an equation we can generally use. And at the bottom, you see the diagram is derived from. It is a line or protected object, normally an overhead line. You can see we've taken a fault location in the line. The fault is at the location M along the line. So M is somewhere between 0 and 1 if the fault is on the line. 0 if the fault is right in front of the relay. 1 if it's at the end of the line, at 0.5 in the middle, and so on. So M is indication. If M is smaller than 1, we are inside, and if M is larger than 1, the fault is beyond the extent of the relay. We assume here the directionality. We do not go to negative M's for reverse faults, because that is a separate issue. The directionality we can, for distance protection, assume it's always going to work, that we can set a zone, say it will be looking only in the forward direction. The top here is then the Kirchhoff voltage loop equation created with the bottom, and it applies to any fault. But remember, you'll always have the relay location where the V loop is measured over there. And from there, the relay will measure the current, the I loop. It will flow outward towards the fault, through the fault location, and then back and come back as a return current. And we must consider both paths, the outward path, MZL, and the return path, Z line return. For a face-to-face fault, it's both times the line impedance. For a face-to-ground fault, it's the line and the ZE. And we have to, obviously, the ground fault will have a different measuring technique to cover for the ZE, which the face-to-face fault is a ZL and ZL. All right, that will come back to this equation later on. It's basically the fundamental or starting point to define how your distance relay in modern terms is going to work. If we, for example, solve this M over here, then we would know exactly where the fault location is. In essentially, but the M would imply that the fault is on the line, okay? So we would have to measure the R fault separately. So once you have extracted M is a location, assuming the fault is on the line. It is just a percentage, remember, and we'd have to convert that back to a location in a characteristic. So that's the interesting thing. You would set a characteristic. So calculating M here is indication inside, outside, but it would not directly be able to give you a cross over here, because remember this cross has got an X and an R. So you have to basically, to plot it into a characteristic, go back to an X and an R. But that is something that we have to just understand in the method of setting the relay. The setting at the relay of the distance relay is still in a characteristic. One has not really gotten to the point where one sets the distance relay simply based on the derived M, because one has to consider the classic approach in that sense. All right, that is the three questions, what, why, and how answered. Now we're going to go on with what we now have at this point. Remember this complex equation, and we're going to a little bit try and understand what are the factors or components to generate or come up with this complex equation, and how the distance protection fits into that. For that purpose, I'm using a simplified diagram here. You can see there's only the output part. It's symbolic now to explain what we are doing. It is not the exact representation of how a distance relay will work, because we don't have the return part here. So it's just for explanation purposes. So the function is going to the distance relay will be set located here. It'll have a set reach, and it will then try and establish, is this a fault inside this set reach or outside? That is the requirements of how it will be doing what it has to be doing. That's its job, so to speak. It will be doing this by measuring obviously voltage and current. You can see voltage and current is measured, and then because it's numerical, we're talking about numerical relays now, it has a complex phasor, so it can take the equation you see on the complete side there, V, the measured voltage is equal, Kirchhoff again, I left times MZL. We have no fault resistance here, so we have a simplified, very simple equation at this side over here. For example, if the M over here is less than 1, it's internal here. For example, M round about 0.55 would be that red dot. And you can see the fault is exactly on the line impedance here. Simple starting point. And clearly, we will trip for the internal fault because it's inside the set reach. If we now come to the problem that we know we will be facing, there is a fault resistance here. This fault resistance now creates some difficulty, because there will be a voltage drop on the fault resistance, not only due to the current coming from the left-hand side through a loop, but also for the current coming from the right-hand side through the loop. We have to look at the sum. I left plus I right will be flowing through the fault resistance. So if we extend our equation here, the equation, remember, it was I left times MZL. That was up to the fault location. We have to include in the voltage loop now the sum of the two currents, I left and I right, and that's a vector sum. You can see vector because there's a line underneath, times the fault resistance is real. It's no phasor, it's just but this sum of these two currents times the fault resistance create a voltage drop. And remember the measurement we used in the simple at the bottom was V divided by I left. The relay only has the I left current for the measurement, and if we divide this top equation by that, we will see here that the fault resistance is appearing as 1 plus I right over I left in the loop. So it is appearing over here. At this point, it's just shown as the real resistance, but you can see this is an assumption which will not always apply, because we have here a complex division, I right plus I left. This would only be true if the angle of I right and I left have the same angle, because then the ratio will be a real value. If the angles are different, you get a complex result, and that complex result would mean that this is going to be tilting up and down the resistance measurement. Looking to that situation now, we take our diagram, we make it a little bit more colorful so we can see what's happening. And we take the fault away, and we take our diagram and replace it with a load condition. So this is before the fault is happening. We're now going into a load condition and trying to see what is happening in this system if we have a load. It's a two-machine model, and if you have a load current, then it's interesting to get real power, because that's what the power system is there for. The load current should be in phase with the voltage. Right, there can be different scenarios. This is a very much simplified diagram, but for explanation, it is perfectly good enough. You can see the load current is shown here in the center, vertical, essentially in phase with the voltage. Okay, so not exactly in phase with the voltage. Why? Because the voltage has got different angles as you go through the system. Because this load current will create a voltage drop across the series impedance. So from the complete left to the complete right, you have to take the total impedance Z sum over here. The Z sum is the sum of all the impedance you see here from left to right. And the voltage drop will essentially, because it's mainly a reactance, this Z is typically an X in a real system. We have a very small R component, it's mainly an X. The voltage is going to be leading the current by 90 degrees, and that you can see that at the top here. That voltage at 90 degrees to the current is there. And that means from the left-hand side to the right-hand side, we have this angle difference. If the load increases, the angle will increase, and the load decreases, it goes down. That is this angle between the two sides referred to as a typical load angle. In a normal power system, we'll see with power swing in the following presentation, not today. In the other presentation, we'll talk about power swings. Obviously, in a stable system, this load angle will be less than 60 degrees. In the extreme situation, typically it'll be less than 40 degrees. And in Western European strongly meshed systems, you can probably get angles which are even much smaller than that, probably in the range of 20 degrees or less. So it is depending on your system. If you have got large distances between generation and load, you can have larger angles, but it's going to affect us. But if we come from this condition now, remember this angle difference here, and we now create a fault, because that's what typically will happen. You'll have load current and then you'll get the fault condition. The fault condition now happening will create the current on left and right hand side to have an angle difference, because the current on the left side will come from the source on the left. Remember the voltage, the internal rotor EMF on the left hand side is the green voltage. We'll have a current, fault current about 90 degrees lagging that, which is the green current we see over here. And the same is happening on the other side, the right hand side. That voltage on the right hand side will have a fault current lagging it by about 88 or almost 90 degrees, depending on the power system. And that means the load angle is essentially defining also the angle between the fault currents from the left and right hand side. That is what we will often talk about, the load influence on the fault. It only comes via the fault resistance, because the influence of the remote fault current is only sensed in the fault resistor. The fault current on the left hand side does not affect the loop as such. It only affects it on this section of the fault resistance here. And that we can see here in this equation. If we now divide the I right by I left, there's an angle difference between the two. And we'll see that on the next diagram. That division I right by I left will create a tilt up and down of the impedance. Complete other side, you can see it over there, tilting up and down of the impedance. If we are exporting load, as maybe from the left hand side, it'll tilt down. If we were importing load, you would typically tilt up. And that you can see in this diagram is a problem. That's why we need to consider the load as such. All right, so we've gone through a few aspects explaining the distance protection localization, how it's going to measure, some of the problems it will be facing. We've used this definition of MZL to localize the fault in the loop equation. We've seen that the load current can affect the measurement via the fault resistance, and ultimately that is the explanation of distance protection. So if we come to this situation now to see how are we going to deal with this requirement, you can see I've rewritten the generalized loop equation at the top here. And you can see that we want to extract M to localize the fault, but there is a problem here. The fault current, which is flowing in the resistance, we don't know. The relay only has available the I loop A current. It does not know the current in the fault. So one needs to deal with this. So somehow this factor at the back here, I fault times RF, these are unknowns. They are inside the loop, but we don't know I fault. And we don't obviously know R fault. And how would we deal with this? It is tilting up and down, as we saw. This We know the reason for that. That's because the two currents on the two sides are not in phase. Again, a different equation at the bottom here. BIA showing you the complex division multiplied by RF. That's the reason why it is tilting up and down. That gives us a delta in the X, and that is not good because the delta in X will be our zone boundary and can give us selectivity problems. Remember, the zone 1 setting, for example, may not pick up on the external fault. So we need to consider that in our safety margin. So we now introduce for the first time the situation that you have to know which type of distance protection you're talking about. You can see at the top in the heading it says classic distance protection. The classic distance protection is going to take this loop equation here and make the assumption that this does not exist. Okay, we can do this and say, all right, let's try and assume that it is not there initially. Then we can solve for m ignoring that, and then we have all the values because the relay can measure all of this. The two currents flowing at the relay location, I loop A out, and the return current can measure, and the voltage can be measured. And then we know the ZL is a setting, so everything is known. We can calculate M. But the problem, the assumption would be that this M is on the line. But we know it's not because of the fault resistance. But the fault resistance, on the other hand, we know will just push the impedance into the first quadrant, as you can see there. So then you apply a setting, and we'll talk about that later on, a resistance reach setting to make allowance for that. So that is the ultimate result. So the classic distance protection will take this and make a resistance boundary setting. So the X boundary, we'll look at that later on, is set for the reach. The R is set to consider the fault resistance. And we know there's some tilting up and down. We have to deal with that in another way, but the classic distance protection can deal with that. And there you can see for the classic distance, for that tilting up and down, you have the choice to set here the zone inclination angle. Okay, and that you would typically use on a zone 1. And in the manual, there's some derivation where you can derive the setting for this angle depending on your load angle. Remember the load angle between the left and the right hand side. Alternative to that, we have a distance protection with RMD. You can see at the top in the heading. This is the reactance method distance protection. It starts with the same equation here, but it is not simply going to assume that this is not existent. It's going to use a mathematical method to compensate for this, to extract it, or a so-called load compensation. And the technique, I don't want to go through it in too much detail. It is complex mathematics. You take a I sub current, a substitution current, and the requirement for the substitution current is that it has the same angle as the fault current. Okay, so if you conjugate that current and you multiply this equation on both sides by that current, you can see it was done here. Makes the equation even a little bit longer. But you can do this, multiply the equation on both sides by the conjugated I sub, and then you take the imaginary component. And then the reason why you do all of this is because then this term over here will be equal to 0. Because the imaginary component of this term is 0, because if I sub and I fault have the same angle, then I fault times the conjugate of I sub will be a real, pure real, not have no imaginary part. So that will be 0. So that technique then, so if you then solve what is left over here, if this is 0, you can see there is no more I fault and R fault in there. We can solve this part of the equation like this and derive M independent of the resistance. This is the so-called reactance method distance protection. There's some difficulty in defining I sub, okay, but it's explained in other presentations and also in the manual. I just have one slide showing here. You have only one setting, because that's really at the end of the day the problem you have. What do I have to set in the relay? There's only one setting here. The setting applies for the ground loop. So in the ground loop, you have the choice whether you want to use the 0 sequence or the negative sequence current as the origin for the substitute current. The phase-to-phase fault will always be done with negative sequence. There's no setting required for that. And then you have compensation angles here. The compensation angles is a fairly complicated equation here. It's for non-homogeneous lines. Again, if you leave it on the default 0 degrees, then you assume a homogeneous system, which will be good enough or much better than doing nothing in 80% of the cases. But we have complicated situations. You can then set a compensation angle to even allow for non-homogeneous systems. All right. So which should you use? Now I've created some new difficulties for you, saying, okay, there are different RMD, classic distance protection. Which one should you select? You can see them here in the global library of Dixie 5. The classic you can use if you have a system with meshed, strongly meshed system like the Western European system over here. We've checked this with the utility over here, some historical data, and we compared. We did not really need an RMD. There was no need for load compensation. The faults were all measured very, very accurately with the classic. The RMD is strictly in countries or in areas where you have got long transmission lines, very large distances between your generation and your loads, geographically extensive distances and long transmission lines, and you get large load angles. That's where the RMD with the load compensation has got a big advantage, where one should use that. Generally speaking, I would say I would recommend to use RMD always. The classic only really where you say, okay, I have historic, I'm using an old application, I'm going forward to my new application, and I want to keep everything is the same as it always was. Then you say, okay, I use the classic, but it doesn't change anything that I had in CPROTEC 4 or even older relays. That would be the advantage. So we almost have everything defined. The X-reach, we spoke about directionality. The directionality is added as a separate measurement to the reach measurement. How is it defined? And here again, I've taken from the manual, the diagram. You can see that reach boundaries are defined fixed. You have basically the 30 degrees in the second quadrant there, and this minus 22 degrees in the fourth quadrant. For the forward reach, those are fixed directional boundaries. They are just defined like that. There is no setting for that. It's fixed. You don't have to modify that at any point. How is that determined and why do we need that? I think we have looked at this a few times. The directional requirement is obviously for the faults when they come very close to the relay location. Here shown the orange little circle there. The faults are very close to the relay. What will happen is the voltage will become very small, near zero. Ultimately, it could even be zero if the fault were a bolted fault right at the relay location. That means if the voltage were, for that condition, theoretically even zero, then you couldn't have no directionality, but it would simply be zero, and zero is zero, and you would not know if it was forward or reversed ultimately. But even for faults close to zero, the tolerances on the voltage would create difficulties, and one would have to worry about that a little bit, and that's why we have a direction measurement independent of the reach measurement. What alternatives do we have for direction measurement? Classically, I've just shown very simple examples here. In the middle, you can see the faulted voltage. Okay, as the fault moves closer to the relay, that VF will get smaller and smaller. And we want to replace it with a substitution, a polarizing quantity for direction measurement. The very widely used technique is the memory voltage. You can see here, you simply say, what was the voltage prior to the fault? I memorize that. And then when the fault happens, I use this memorized voltage for directionality. Because the directionality only needs to know angles, really. Is it in an angle range forward or an angle range reverse? So the magnitude doesn't matter. So the requirement then is obviously that the memory or the basically polarizing voltage has the same angle or a similar angle. We have large tolerances. You see, that's why you see the reach boundary going 30 degrees into the second quadrant and 22 degrees into the fourth quadrant. You have the directional boundaries are tolerant. They are not restrictive around the fault. To make allowance for any influences like this, it's not critical. So that is an important thing. An alternative to the memory is what is shown on the left there, the healthy phase. We did speak about that. Remember the Mohs circle, you had the choice, use memory voltage or healthy quadrature phase. The quadrature phase obviously does not apply to three-phase faults. Three-phase faults are a little bit difficult. But for all other asymmetrical faults, you will find a healthy phase, but either a phase 1 to ground fault, as we see here. The voltages L2 and 3 are healthy. They are not affected. And you can see the phase-to-phase voltage, 2, 3. If you rotate that by 90 degrees, you get that yellow phasor. And that yellow phasor can be used to replace, for example, the memory voltage. It's got the same angle as the memory voltage, can be used as a polarizing quantity. That's when we talk about direction measurement, you'll also sometimes hear other polarizing techniques. There are delta techniques and so on. There are a number of them. but one very common one is the symmetrical components. I've taken just a symbolic diagram over here. Phase A to ground here in symmetrical components, top positive, negative zero sequence system. And we would use maybe the negative or the zero sequence system, one of them, to do directional decision. And you can see here the fault location from where the relay is located over here. The fault is over here, a forward fault. And under these forward fault conditions, this I0 and V0 will give you a certain angle definition here. You can see which is clearly defined. And interestingly enough, it's independent of the fault resistance. This is a very, very dependable and very accurate direction measurement here, and it can be done in a very clear angle range. And the angle between these two is defined by the angle of the source impedance here. And exactly the same you could do in the negative sequence with a forward fault location. If the fault moves to the reverse, remember then this point will be behind the relay, and what will happen, this current will reverse here. The current will flip over to the other side, and you have a 180-degree switch between forward and reverse. Very, very dependable. The symmetrical components are a very, very useful tool to give you information about asymmetrical faults. All right. Ultimately then, that technique, whichever one is used under, and you don't have any settings to worry about there, it is done automatically, will give you these two boundaries. So we'll have a reach setting, we'll see that later on. We'll have a resistance setting, which we'll talk about how to set the resistance reach. And then we have direction fixed by the direction measurement, and then all boundaries, all zone ends, sides of the characteristic are defined.